Hello everyone, welcome to my video on optimization. So up until now we have the necessary tools required to solve optimization problems. So optimization problems closely resemble related rates problems. So related rates, when you're solving those types of problems, you're coming up with an equation and you're taking the derivative with respect to time. But that equation could have multiple parameters. You could have x, y, and z. Optimization is different. You're creating an equation, but your equation has to be expressed in terms of a single variable, only one. And then you're going to take the derivative with respect to that variable and set the equation equal to zero. Because we know that when when a function has a maximum or a minimum, its derivative is equal to zero. So behind me is a strategy that we're going to use to solve optimization problem. So the first step, read the question carefully as always, and identify your variables pertaining to the situation. Okay. Step 2, super important, take the time, draw a sketch of the situation. 3, write down the equation and express it in terms of only a single variable, as I mentioned. So we're going to write the equation in terms of a single variable, take the derivative of that equation that needs to be optimized and set it equal to zero. So let's say you're trying to maximize the area of land for a garden in your backyard. You want to maximize the area. Since we're dealing with area, it's the once you create the equation of an area, that's what you're going to take the derivative of, because that's what you're trying to maximize. Okay. So once you take the derivative, we set it equal to zero, and then we solve for our variable x, and we have to check the domain. Okay, so it's really important to check the domain as well, because let's say you're creating your garden, you have your area of your garden, and you want it to be as small as possible because you want your garden not to take up too much area in your backyard. Well, you're trying to minimize the area of the garden. So if you're trying to minimize it, you have to ensure that the answer you're getting is actually a minimum and not a maximum, because here we're talking about optimization. Are we dealing with a max or are we dealing with a min? We have to know which one we're getting, what our answer represents. So if you want to maximize your garden, you have to ensure that this is in fact a maximum and not a minimum value. Okay, that's why it's important to check the domain. Let's look at a couple of examples. So here I'm providing you with a formula sheet that you're gonna have memorized. So pause the video, make sure you're comfortable with these equations, and we're gonna need them in order to solve optimization problems. Okay, so in this example here, we have a farmer which has 120 kilometers of fencing and wants to fence off his rectangular land. What are the dimensions that will maximize his area? So let's go ahead and do this. So we have this keyword 120 kilometers of fencing. What does that correspond to? You have to think about that. And he wants to fence up his rectangular land, another keyword. So let's go ahead and draw the shape. We're dealing with a rectangle. Okay. And what does the 120 kilometers of fencing refer to? Well, if we look at the units, it's kilometers. And when you're fencing your land, it's all around. So we're really dealing with perimeter. So what he's telling us is that the perimeter is 120 kilometers. And we have to label our length and width. Let's call this the length, let's call this the width, x and y. Okay, so very important to label your drawing. We have two variables here, we have x and y, so keep that in mind. And it's asking what are the dimensions that will maximize, another keyword. We want to maximize what? The area. Okay, so we have to find the area of this shape, the rectangle. So the area of a rectangle, we know the formula is a equals x times y. And since we're trying to maximize the area, it's the area that we're going to take the derivative of. Okay, so whatever you're trying to optimize, that is the equation that you have to take the derivative of. The issue with it right now is we can't take the derivative yet. If you're thinking of using product rule with implicit, you can't do that here. For optimization, we have to express this as a single variable. So we cannot use this, not yet at least. Okay, because of the two variables. We have to substitute, switch one of the variables. Typically I stick with the x, but it really depends on the problem. You could stick with x or y, it's up to you. So we have to come up with a second equation. What information haven't we used yet? Well, we haven't used the perimeter. So let's go ahead and create a new equation, or not a new equation, a second equation with involving the perimeter. So we know that the perimeter, and this is why it's important to draw. A common mistake is students write that the perimeter is equal to, without the drawing, they write x plus y. Okay. So be very careful when you're finding the perimeter, you're adding up all the sides. So there's not one x, it's 2x plus 2 y's. Okay, you have a y here, you have a y here, you have an x here, an x here. So it's 2x plus 2y. This is a common mistake, and I think by drawing it, you could avoid making silly mistakes like that. But anyways, this is our new equation that we have. We have x, y, and we know what the perimeter is. They give us that the fencing, the amount of fencing is 120 kilometers. So our p is 120. So what we could do now is solve for one of the variables, either x or y, and then substitute it into the area formula, allowing us to express it in terms of a single variable. That's the game plan. So here I could solve by, let's solve for y. I could solve for y by dividing both sides of the equation by 2, giving me 60 equals x plus y, and then subtracting over the x. So 60 minus x equals y. Okay, this is my first equation. This is my second equation. Now we know that y is equal to 60 minus x, so we're going to substitute it into this equation. So now we know that the area is equal to x times y. But what's y equal to? Y is equal to 60 minus x. And now we have an area formula that's expressed solely in terms of a single variable, x. Now we can take the derivative. So let's go ahead and do that. Let's begin by simplifying. So I'm going to distribute the x, giving me 60x minus x squared. Oh, that's not the derivative. That's just the simplified version. So I just simplified it. Now next step, let's take the derivative. So if I'm taking the derivative with respect to x, so I'm just going to write a prime. If you want, you can write a prime of x. It's expressed solely in terms of x. Taking the derivative of this, we get 60 minus 2x. And we know that the game plan for optimization problems is taking the derivative and setting it equal to 0, right? So we're going to set this equation here equal to 0. And now we're going to solve for x. So I'm going to bring the negative 2x over, so 60 equals 2x, and then we're going to divide both sides by 2, giving me 30 equals x. So the length over here is going to be, well, let's keep the x, it's going to be 30 kilometers. Okay, and what's the y going to be? Well, we know y is equal to 60 minus x, so we just substitute it back in. We get 60 minus 30 is equal to y, so y is also 30. And there we have it. The dimensions that are going to maximize the area is if the base is 30 and let's say the height is 30. So essentially what we have is a square. Although it says the rectangular land, you have to keep in mind squares are rectangles, rectangles are not squares. So having the answer be a square is perfectly fine, and that's the optimal solution. This is going to maximize the area. Okay, so we found our answer, but we have to ensure that this is in fact a maximum. How do we know it's a maximum? Well, you might know from, or you might remember from high school, that to maximize the area of a rectangle, the square is the optimal solution, which is true. But let's go ahead and prove it using derivatives. So let's check the domain. First things first, we're talking about distance. So x has to be greater than 0. Right? We can't have a negative distance. Equal to 0 doesn't really make sense, but for now, I'll keep that. You could have a width that's nothing. Not really interesting, but let's keep it for now. And secondly, we know that the area has to be greater than 0. Right? We can't have negative area. So the area formula that we have is 60x minus x squared. So we know that 60x minus x squared has to be greater or equal to 0. Factoring out an x, we get x times 60 minus x has to be greater or equal to 0. Since x is already positive, we stated that up here. This is positive. In order for this statement to hold, the 60 minus x has to be positive. So for this to be true, that means 60 has to be greater or equal to x. So x has to be greater or equal to 0, but at the same time smaller or equal to 60 in order for this problem to hold. So that means our x is in between 0 and 60. Okay. So if our x is between 0 and 60, what's the maximum area that we could have? Let's check. This is essentially a closed interval. So we're applying here the closed interval theorem or method. We have our closed interval here, so we attain a max and our min. Let's go and ensure that this is in fact a maximum. So we could test the endpoints and we could test the critical point. We got the critical point, x over here equals 30 is essentially a critical point, and because we took the derivative, set it equal to 0, same concept. And we know that the area, if we plug this into the area, we get 60. So remember, we're using the closed interval theorem here, or the extreme value theorem, so we're plugging it back into the original function, not the derivative, okay? Because it's on a closed interval. So if we plug in 30 into the area formula, we get 60 times 30 minus 30 squared. This gives us, let me use a calculator, 900. Okay. Whereas if we plug in 0 or 60, a of 0 is just 0, that's obvious. Because if you plug in 0 here, 60 times 0 minus 0 squared is 0. And 60, if we plug in 60 in here, we get 60 times 60 minus 60 squared. So 60 times 60 is equal to 60 squared. It's the same thing, so this is just 0. So we do in fact have a maximum value. Okay, because we checked the critical point and we checked the endpoint, so this is an absolute max. So we ensure that this is in fact an absolute max. This is one way of doing it, where we applied the closed interval method or the extreme value theorem. Another way you could have done it is using the second derivative test. So let me just show you a second method. Let's erase this. So to show that it's in fact an absolute maximum, we can use the second derivative test. So what's the second derivative equal to? Well, we found the first derivative, it's equal to 60 minus 2x. If we take the derivative of 60 minus 2x again, we get just the second derivative equals negative 2. We know that the second derivative at the critical point, or the inflection point, is giving us the concavity. And since this is always negative on the interval, it's concave down. If this function looks like this, it's a quadratic and it's concave down, we know that our f prime of c, or in this case our f prime of x, which in our case, in terms of this problem, is our a prime of 30, is in fact a maximum, okay? Because the concavity is downwards. So this is an absolute max. Okay. So that's another way of checking to ensure that your answer is in fact a maximum. So this next example is very similar to the one we just saw, so pause the video, try to do it on your own. We have a farmer which has 120 kilometers of fencing again and wants to fence off his rectangular land. But the catch is that his land borders a river now. So wherever there's the river, we're not putting a fence, we're going to leave it open. What are the dimensions that will maximize the area in this case? Okay, so let's go ahead and do it. First off, let's draw a sketch. We have our river on the bottom. So we have something like this. This is the river. And this is where we're putting the fence now. Let's label our sides, calling this X, and let's call this side Y. And again, we know that the perimeter of the fencing is 120 kilometers. The question is asking us to maximize the area, so we know that we have to take the derivative of the area. The area of the shape is again a rectangle, so it's still x times y. This is what we want to take the derivative of. Again, we have to express this solely in terms of a single variable. Here right now it's 2, so we have to either change the x as a y or change the y as an x. And again, it's up to you. So let's go ahead now and find the perimeter. What changes? So the perimeter now, looking at our sketch, this is why it's really important to draw. It's not our typical rectangle because we're not bordering the bottom of the rectangle. So in this case here, when we talk about the perimeter, the formula is going to be 2y plus x, right? Because the bottom's open. So we have 120 equals 2y plus x. And now what we do is we either solve for x or for y. So if you want to bring over the 2y and replace your x with 120 minus 2y, that's fine, you could do that. I'm always gonna solve for the x. I prefer it that way, so I'm gonna go ahead and do it that way. So solving for y, I'm substituting y here to write the area, express it solely in terms of x. Okay. So I'm gonna start off by bringing over my x by subtracting x on both sides. So if I bring over my x, it becomes negative x. We have 120 minus x equals 2y, and now I'm gonna divide both sides of the equation by 2, giving me 60 minus x over 2 equals y. So it's not as efficient here because we're working with a fraction, but that doesn't bother me. So I'm going to go ahead and do it this way. Now I'm going to substitute my y with this equation. So we have the area is equal to x times, in brackets, 60 minus x over 2. Same process as the previous problem that we saw. and now I'm going to go ahead and distribute your x. If you solved it on your own and you got the y, you went in the y equation, that's fine. We'll end up with the exact same dimensions. So the area is equal to 60 times x. I'm distributing the x now, minus x squared over 2. And now we go ahead and take the derivative, now that it's expressed solely in terms of x, or a single variable. So the derivative is equal to 60, here it's power rule minus x. Okay, we took the derivative, set it equal to 0. This means that x is equal to 60. Bring that over, we're done. So we found the value of x, it's equal to 60. Let's go ahead and find y. This is 60 minus 60 over 2 equals y. 60 over 2 is 30, 60 minus 30 is 30. So y is equal to 30. Okay, so this is the dimensions of this rectangle that will maximize its area. Okay, we have to ensure that this is actually a maximum. So let's go ahead again and check the domain. Y is 30. Let's go and check to ensure that this is in fact the max. So the method here that would probably be easiest to do is probably the second derivative test, because we have the first derivative here. So if we take the second derivative, the derivative of 60 minus x is just -1. So again, the concavity is downwards. So the function's looking like this. So we know we have an absolute max. Okay, because it's negative on the entire domain. Okay. So that's one way of doing it. The other way of checking that it's an absolute max, let's do it the other way as well. Let's go ahead and get the domain. We know that the value of x has to be positive again. We can't have a negative distance. And we know that the area has to be positive. We know that the area is equal to 60x, or I could write it this way. X times 60 minus x over 2 has to be greater or equal to 0. I'm just taking this form, not this one here. And we know that already x has to be positive. So this part is positive. So in order for this statement to hold, this piece is positive. So we need the 60 minus x over 2 to be positive. Okay. This part's positive because of our first statement, the fact that x has to be greater or equal to 0. Next, what we have is this statement. Let's bring the negative x over 2 over. We get 60 is greater or equal to x over 2. Multiply both sides by 2. X has to be smaller than 120. This tells us that the x lies in between 0 and 120 in order for this statement to hold. Okay, not to have negative areas or negative distances. So again, we have a closed interval. So we can use the closed interval method. We have to check the critical point at 60, and we have to check the endpoints at 0 and 120. So because here we're checking, we're using the extreme value theorem, we're plugging it back into the original area formula. So a of 0, plugging in here, we get just 0. A of 60, the critical point, gives us 60 times 60 minus 60 squared divided by 2. This gives us a value of 60 times 60, 3,600, minus 60 squared divided by 2, 1,800. So this gives us 1,800. Okay, some positive value. And then if we plug in 120, well, here we have 60 times 120, minus 120 squared divided by 2. And this gives us 0. Okay. So since this is 0, this is 0, this is the absolute max value at 60. So this is in fact an absolute max. And we're done. So the dimensions that will maximize the area are, let's throw in our units because everything's in kilometers here. Dimensions are, let's say, 30 kilometers by 60 kilometers. That would be the final answer. So in this example here, it's asking us to determine the largest rectangle that can be inscribed into the parabola y equals 12 minus x squared, such that the rectangle lies in quadrants 1 and 2. So pause the video, try this on your own, see if you can get it. The first thing we're going to do is go ahead and draw the function. So let me draw the function in green. It's a parabola. It has a highest value of 12. When you substitute the value x with 0, you get 12. And since the coefficient of the x squared is negative, it means it's concave down. It's opening downwards. So it's going to look something like this. Okay. And let me draw it in red. We're dealing with a rectangle. What's the largest rectangle that we could put here? Within quadrants 1 and 2. So remember your quadrants. This is quadrant 1. This is quadrant 2. This would be 3 and this would be 4. So what's the largest rectangle that we could have inscribed in our parabola, but still within the first two quadrants? This is what the question's asking us. Okay, let me just put this as x and y. And this is the point 0, 0. Okay. So we're dealing with, in red, the area of a rectangle. Let me write that down. Because it's asking the largest rectangle. So we're really talking about the area of the rectangle. So if you go ahead and solve using this equation, area of a rectangle is x times y, you're actually going to get the question wrong. That's why it's super important to sketch the function, put a drawing in it. Because if we think of this in terms of a Cartesian plane, well, this corner here could be expressed how? Well, if this is the origin 0, 0, from here to here, this distance here is your x, and this distance here is your y. So this is the point xy, right? Meaning that the height of the rectangle is y. That's fine. That's y. But what's the length of the rectangle? Well, it's not x. In this case here, x would be from the middle, from the origin to this point here. The entire length, the entire length would be 2x, because this is negative x, this is positive x. If you think of this as the point, this is the point negative xy. So the distance from x to negative x is actually 2x. So this is 2x, meaning that the formula that we're using here is not a equals x times y, it's actually a equals 2x times y. Okay. So very tricky. Make sure you don't fall for these. So always draw a diagram. I'm telling you it's going to help. So we get the area equals 2x times y. Again, we have to express this in terms of a single variable. So what else could we use? Well, we want to get rid of the y. What's the y equal to? Well, they give us the equation. Y equals 12 minus x squared. So we're going to directly substitute the equation of a parabola into our function. So we're going to express the area as a equals 2 times x times 12 minus x squared. Distributing the 2x, we get the area is equal to 24x minus 2x cubed. Now we're going to take the derivative with respect to x, so a prime of x is equal to 24 minus 6x squared. Set the derivative equal to 0, we get, let's go ahead and factor out a 6, leaving us with 4 minus x squared. And in the bracket, notice that we have a binomial separated by a subtraction sign. So this here, we could apply difference of squares. So we get 6, 2 minus x, 2 plus x equals 0, right? Because we could square root 4, we could square root x squared, apply difference of squares. And now we use the zero product law. So either the 2 minus x equals 0 or the 2 plus x equals 0. So 2 minus x equals 0, meaning that x equals 2, or 2 plus x equals 0. Bring the 2 over, we get x equals negative 2. Okay. So this x value here is 2, this one here is negative 2. So that gave us information. Let's go ahead and find the y. So to find the y, we just plug it into the original equation. We know x is 2, so 2 squared is 4, 12 minus 4 is 8. So this is 8. So this is the point 2, comma 8. Okay. So now we have to go get the domain. So we found the maximum, the value of the x and the y. The question is asking us to determine the largest rectangle or the largest area. So we have to actually answer that question. So the largest area would be a equals 2 times x times y. So 2 times 2 times 8. So the largest area, 2 times 2 is 4, times 8 is going to be 32 units squared. Okay. So that's the largest area. We just have to ensure that it's actually a maximum. How do we do that? Let's check the domain. Know that the domain of this function over here in green goes from, it has to lie in the first quadrant, so it's going to be, let's say, from this point here to this point here. Okay. What do we know about these points? Well, they lie on the x-axis, which means that their y's are 0. So we could take the green function here, which is y equals 12 minus x squared, and substitute the y's with 0. We bring over the x squared, we get 12, and then we square root both sides. X equals plus minus the square root of 12. Okay, which we could write plus minus. 12 could be rewritten as square root of 4 times 3. So we could rewrite this as 2 root 3. Okay, plus minus 2 root 3. So this is the x value for these 2 points. But we know that the coordinate point is negative 2 root 3 comma 0 and positive 2 root 3 comma 0. If we go ahead and find their areas at these points here, the area, because we're incorporating the y, which is 0, when you're multiplying by y in our formula, it's going to just give us an area of 0. So so essentially, first of all, let me just mention that the domain is the x values from negative 2 root 3 to positive 2 root 3. That's the domain where the function is defined. And it's a closed interval, so we could check the critical point, which we found was at negative 2 and positive 2, and we could check the endpoints as well. When we plugged in negative 2 and positive 2, we got positive 32 over here. And now we just have to check at these 2 values. But when we know that the y values that correspond to these x values are 0, meaning that when we plugged into the areas, a of negative 2 root 3 is just 0, and a of positive 2 root 3 is just 0. Okay, so that means that this value here is the maximum. This is actually an absolute maximum. So we're done. So in this example here, we have a box in the shape of a square-based prism, which is being wrapped using expensive wrapping paper. So the top of the box costs $2 per meter squared, the sides cost $3 per meter squared, and the bottom costs $1 per meter squared to wrap. The volume is 4 meters cubed, and they asked us to find the dimensions that will minimize the cost to wrap this box. So let's begin by sketching our shape. We're dealing with a square-based prism. So let's draw that. This is important because keyword here is square. So if the bottom is x, then the side has to be x as well, because we have the base is a square, right? So they have the same dimensions, and the height didn't tell us anything about the height, so we'll just call it y. Okay, and then they tell us that the top of the box costs $2, so this part is $2. All the sides are $3 per meter squared, and then the bottom of the box is just $1 per meter squared to wrap. So they tell us that the volume is 4 meters cubed. This is important information as well. So they're actually giving us the volume. And lastly, they're asking for the dimensions to minimize the cost. So we have to go ahead and minimize the cost. So they mentioned the volume, so let's go ahead and write our volume formula. Volume equals length times width times height, because we're dealing with a prism. But the length and the width are x, so we'll call it x squared times y. Okay. What's important here is the fact that they're asking us to minimize the cost. So the function which we're optimizing is a cost function. We have to create a cost function because that's what we have to take the derivative of. You're not taking the derivative of the volume, okay? So we have to find the cost function of x. So how would you figure out the cost to wrap this box? We know the volume is equal to x squared times y. We know that the volume is 4, so they actually gave us an equation, 4 equals x squared times y. We'll keep that on the side. But here for the cost function, how are we going to express it? Well, to figure out the cost to wrap this present, Well, the top is going to cost us $2, but what's the area of the top? It's $2 per meter squared. We're essentially finding the surface area of the shape. So the surface area of the top of the shape here, it's going to be x times x. This is, if the bottom's x, this is x. If this side is x, this is x. So the top is x squared. But since we want the cost, it's 2 times x squared. Okay, so whatever the area is here, you're multiplying it by $2. Okay, so 2 times x squared. The sides, the area of one side is x times y. How many sides do we have? 4. So we have plus 4 times x times y, because we have 4 sides, but then multiplied by the cost, because we're dealing with the cost, so times 3, because the sides, to wrap the sides, it costs $3 per meter squared. So if we multiply by 3, this gives us 12 times xy. And then lastly, we have the bottom. And the area of the bottom is x times x, which is x squared, times the cost, which is 1. So 1 times x squared. So I'm just going to write x squared. And this is our cost function. This is going to enable us to find the optimal cost to wrap this box. Okay. So since this is the function which we're going to take the derivative of, let's just simplify it. C of x equals, we have 2x squared plus x squared, that's 3x squared, plus 12xy. The issue is that it's not written solely in terms of one variable. We wanted to express it solely in terms of x. Here we have a y. How do we fix that? Well, this is where we use the volume formula. So we solve for y by dividing by x squared. 4 over x squared equals y. So there's a bit of an issue here. We're dividing by x squared, but we know that x cannot be equal to 0. So there's no issue with worrying about dividing by 0 here. So x cannot be equal to 0. We have 4 over x squared equals y. So we're going to substitute the y with 4 over x squared, giving us 3x squared plus 12x times 4x squared. This is c of x. And this is giving us 3x squared plus 12 times 4 is 48 over x. So this is our cost function. We're going to go ahead and take its derivative. So I'm just going to give myself some room. This was used. So let's go ahead and find the derivative of the cost. So c prime of x. So the derivative of 3x squared is 6x, and the derivative of 48 over x, we could think of this as 48 times x to the negative 1. So if we think of it as 48 times x to the negative 1, this is really just minus 48 x to the negative 2. So we just applied power rule. If not, you would have to use quotient rule, which is fine as well. Okay, so we get this, and we set the derivative equal to 0. 6x minus 48. We could drop the x squared, write it this way, bring the negative 48 over, giving us 48 over x squared equals 6x. Cross multiply, giving us 48. I'm going to divide by 6 right away, and multiply the x squared on top, giving me x cubed. 48 divided by 6 is 8, so I'm running out of room, so I'm just going to write it here. 8 equals x cubed. And lastly, we have to find the value of x by cube rooting both sides, giving us 2. So x equals 2. The value of x here is 2. Now we have to find the value of y. So I erased the equation, but y equals 4 over x squared. It's right here. Y equals 4 over x squared. That was from before, our volume formula. And we know x is 2 now. So this is 4 over 2 squared. 2 squared is 4. 4 divided by 4 is 1. So the x value is 2. Let's put the units, 2 meters. And the y value is 1 meter. Okay. So the dimensions to minimize the cost is going to be the base here 2 by 2 by 1 meter. Okay. And that's the answer. So let's just go ahead and ensure that this is in fact an absolute min. This is the minimum cost. We could do that by testing values. Our critical value was 2. So let's go ahead and test points to the left and to the right of 2. So let's try 1 and let's go try 3. By plugging these values into the first derivative, what does that give us on the function? So the first derivative, which I'll call c prime of x, and this would be c. Plugging in 1 into c prime of x, into this we get 6 times 1 minus 48 times 1 to the negative 2, which is just 6 minus 48. This gives us a negative value. And then if we plug in 3 into here, in this equation here, we get 6 times 3, which is 18 minus 48 divided by 3 squared, which is 48 divided by 9. So 18 minus 48 divided by 9, and that gives us a positive value, meaning that the function, the cost function, is decreasing beforehand and then increasing after the 2. So we have a local min. Okay, so we have this is in fact minimizing our cost function. Okay.